Hello, folks. This is the Fatty Liver Foundation and Array Insights webinar for the day. We'll give people a few minutes to connect here, but for everybody that's already come on, we're glad to have you, and we'll be in the program in a minute or two. We certainly appreciate you joining us today. This is a subject that has rattled, is rattling the world right now. And we thought we'd give you guys a little inside baseball look at what goes on. We'll give a few more seconds here before we actually talk about meaningful things. Well, let's get this rolling. It is recorded, so people can see the front end if they turn up late. And so welcome everybody to this webinar. It is being recorded. We'll send out a recording to everybody that registered. And you can see that on our YouTube channel. Next slide. So many of you know my story. I'm Wayne Eskridge. That's the picture of the typical American guy that I was. You know, most people find themselves in these situations by accident, really. We don't think of ourselves as being unhealthy or developing bad things. We get out, you know, and when we're young, we're active and busy and doing things, and the temptations of food get to us quickly. And over the years, we normalize how we see ourselves. And, you know, I look at that picture now from 1995, and, you know, that was, I was born in 42. So, you know, I was getting on into my 50s there. And I gained a pound or two a year for 50 years. And, you know, I didn't think anything about it. And I never saw myself as someone who had to lift up their belly to do their belt. I honestly never, ever, ever had that thought until some years later when I saw this picture. But that's what's happened to our society, and one of the reasons that so many of us have this disease. So we've all heard the stories of, you know, what we should do better and all of that. So I won't go into that. But you know, I lost basically a third grader when I got myself under control, and I'm doing well. So next slide. Today, we're going to be joined by the Array Insights team. They'll introduce themselves more specifically as we get to it. But Array is one of the leaders in a branch of this new AI machine learning arena that we find ourselves in. And it's really important to healthcare. And one of the things that I would like to say clearly is there's a great deal of confusion and fear about machine learning, AI. You know, it's going to kill us all. It's going to turn us all into servants. It's going to destroy the world. We believe that AI and machine learning will be an unambiguous benefit to healthcare. there'll be issues, there'll be problems to solve, no mistaking that. But it's going to be something that is going to change healthcare, the way we research it, the way we manage it, the way patients interact with doctors. And those are going to be valuable things. And that, that's how we view it from the inside. So next slide. I'm going to turn this over to our Chief Medical Officer, Niraj, so take it away.
Wayne, thank you. And no matter how many times I hear your story, it's always so moving to see what you've achieved. And that gives me a lot of hope from a sort of very medical, technical point of view, but also a societal point of view. So thank you. I just want to check in. My colleague Henry has his hand raised. Henry, was there something urgent? No. I guess we can come back to Henry in case there's anything we need to address. So my name is Niraj Mistry. I'm a public health physician, and I'm the Chief Medical Officer of the Fatty Liver Foundation. Over the years in my global public health career, I have been involved across many infectious diseases. And I think we learned a lot of lessons with infectious diseases. But as we have industrialization in the world, and we're talking about low-income countries, middle-income countries, and in very industrialized countries across Europe and North America, what we're seeing is this entire explosion of what we call non-communicable diseases. This is non-communicable in that it's not an infectious agent that's causing the disease, but it's a disease of lifestyle. And when we look at the fact that most of us email for a living, we all sitting behind some sort of desk, we live very sedentary lifestyles. The diets we have and the exercise and physical activity we engage in predisposes to many issues. So in the next few minutes, I'm going to give you a crash course in hepatology, particularly around NAFLD and NASH. NAFLD being non-alcoholic fatty liver disease and NASH being non-alcoholic steatohepatitis. And this might actually go through a name change, but just an overview of this. So it's estimated in the United States that close to a quarter to a third of the population actually have some form of non-alcoholic fatty liver disease. And I'll go into what that particularly means. And of that, we have a high proportion, anything between 4 to 14% of the general population that have more advanced form of that disease, which is called NASH or non-alcoholic steatohepatitis. I'm just going to use the abbreviations from here on out. And this is essentially fat accumulation in the liver, which then causes a whole lot of other consequences when this happens. Now, when we look at NASH, it's associated, NAFLD and NASH, it's associated with many issues. So it's genetic inheritance, obesity, and I'll just give a few comments on this. When we look at genetics, it's not necessarily a death sentence, because what we're learning more in medical science is that we can influence the expression of genes, and that's with our environment. And this is a whole field called epigenetics. So genes don't necessarily mean that someone's definitely going to get this. It depends on what issue it is. But we also find it's a wonderful interplay between the nurtured environment and the natural environment that people inherit through their genes. Obesity is on the increase, and it has been steadily increasing over the past few decades. The last State of Obesity report in the United States showed that over 40% of the general adult population is obese. And that's not overweight, that's obese. So it's the body mass index above 26, which counts as obesity. The other frightening part of this is that there's a rapid increase in childhood obesity as well. That's starting to catch up. Side effects of medications. We use a lot of medications in society, and they have impacts on the body, not just the medication itself, but medications in combination. rapid weight loss, and this is just with a precipitous drop in weight. It's not the type of weight loss that people generally experience, but when fat is lost from tissues, it gets into the bloodstream and all over the body, and it can accumulate in the liver, and that links to fats in the blood. But many people, not just because of their diet, but the way they metabolize fat can be affected and cause an increase in cholesterol and lipoproteins. And then diabetes is a huge challenge, particularly type 2 diabetes, which is non-insulin dependent, and that's the acquired form of diabetes. But the interesting thing about fatty liver disease and diabetes is that it's a cause and effect of each other. So a lot of these diseases tend to be mutually reinforcing, what we call comorbidities. Okay, next slide, please. So this slide looks quite complex, but I'm just going to walk you through it. So on the left-hand side, we have a healthy liver. And then with obesity, diabetes, and all these comorbidities, we have accumulation of adipose tissue or fat, which is in the bloodstream, in the diet. And then what happens is it accumulates in the liver. And first we get isolated steatosis, which means just little small spots or foci of liver accumulation. But when it reaches a critical mass, what happens is it causes the cells to explode, or it causes irritation in the liver. And that induces inflammation, which is anything with inflammation is an itis, and in the liver, it's hepatitis. So that's non-alcoholic steatohepatitis. And just like when we get a cut on our hand and there's inflammation and it forms a scab, in the liver, it forms a huge scab, which is what we call fibrosis. And fibrosis can lead to failure of the liver, which is cirrhosis, and can also predispose to liver cancer. Now, the important thing about understanding this sort of continuum is that at any point, any lifestyle change can halt or reverse the progression of the disease. And with different ethnic groups and race groups, we find that the acceleration across this progression cycle also varies. And so once again, to reiterate that this is not a death sentence, but we can intervene all along the way. Next slide, please. So with that inflammation that we talk about, there's a lot of research being done on which came first, the inflammation in the liver, or in the inflammation in the body, the inflammation as a result of fat that starts off in the liver and moves across, et cetera, et cetera. And so it's very cyclical when we think about this. And there are many conditions like polycystic ovary disease, diabetes, inflammatory bowel disease, cardiovascular disease that tend to be associated with. And so we like to often think about NASH as a collection of these comorbidities, which in and of itself result from the comorbidities, but they can also exacerbate and perpetuate the comorbidities. And so that's important to bear in mind. Now, I think let's move on to the next slide. So what we talk about NASH being is a perfect storm of all these environmental and lifestyle conditions. And because everyone is so focused on the comorbidity, they're missing what happens when we start putting all these comorbidities together. And this is what we call the perfect storm, or the gathering storm of NASH. So because there isn't awareness about NAFLD and NASH, just about the comorbidities, no one's paying attention to that. But if we let this progress without addressing it, what happens is the costs of hospitalization, of liver transplants, of managing chronic liver disease are much, much higher than the costs of prevention on addressing lifestyle issues, diet, exercise, weight loss, etc. And so because it's off people's radars and there's attention being paid to the comorbidities, we're finding a huge gap in this. And so our mission at the Fatty Liver Foundation is to raise awareness of this and actually be supportive of the interventions that we can do on NASH. Next slide, please. And this is sort of public health school 101. When we think about disease, what causes it and how do we make a difference in people's lives? Everyone always falls, or their default is, well, we need better medical services. But when we look at the influences on health and well-being on an individual, medical services actually and healthcare only account for about 10% of a person's well-being and health. And we look at environmental and social factors, and we look at individual behavior. 40% of an individual's behavior account for their health and well-being. That's huge, as well as genetics. And genetics is very linked to the social and environmental, as well as the individual's behavior. So, for example, if someone has a predisposition to develop lung cancer with particular genes, if that person smokes, their risk becomes much, much higher of developing the disease. So there's a very strong interplay with all of this. And in particular, this circle has a huge role in non-communicable diseases that we're dealing with. Next slide, please. And so if you're feeling overwhelmed by the complex picture of causation, correlation, and association, that's the intent of what I'm actually describing with NAFLD and NASH. Many, many factors. People with higher education versus lower education levels, people with different types of access to food, the community support structure, the economic conditions and health access, education and environmental conditions that we're dealing with all have a role to play in the development of NAFLD and NASH and the management of the comorbidities. Now, when you look at this complex picture, the traditional way in which a doctor drew a diagram that this is causing that doesn't apply anymore. We need a much more complex framework to collect data, to understand it and analyze it, to detect trends and patterns. And this is where this entire world of machine learning and AI comes in. And with that, let me hand over to my colleague Anne to take it from here.
Thank you, Dr. Mistry. Yeah, and the point that Dr. Mistry was making about the complexity and comorbidities of NAFLD-NASH and other diseases like it that are related to lifestyle means that you necessarily need to have larger and diverse data sets in order to better represent all patients who are affected by these diseases. And so I think what's important to emphasize is that when you're thinking about getting more data sets and more diverse data sets, creating larger volumes of data, you have to have a careful balance of not only utilization of this data set, but also protecting the privacy and the trust of patients who create this data, right? Patients like Wayne and others are trusting patient advocacy groups, hospital, physicians, and also researchers with that data. And I think it's extremely important that we take that very seriously. I have a couple of article headlines here noting some abuses of data and also like patient information that are extremely famous. And we need to have protection in place such that we have less liability for handling these types of data sets, but then also really emphasizing the fact that patients really matter and being able to have diversity and representation in these models that are creating any sort of risk stratification or recommendation for better care for these patients. And so there are a lot of ways that you can do this from a regulatory standpoint. We see GDPR and HIPAA and CCPA taking hold internationally, but there are also technical ways of being able to work within the constraints of these regulations in order to have this balance of utilization and diversity and volume of these data sets, while also being able to protect patient privacy. And so I'll hand it off to my colleague, Adam, to talk about the technical ways that you're able to do privacy preserving analysis of these data sets, which has implications of being able to make larger, more diverse and representative models.
Hey, thanks, Anne. Hey, so my name is Adam. I'm a senior machine learning scientist at Array Insights. I have a master's degree in advanced security and digital forensics, and I've just submitted my PhD thesis in privacy preserving machine learning. So just now I'm going to be talking about just briefly what is AI, then a brief history of the data industry, as well as some opportunities and some challenges with respect to the healthcare industry in particular. And then I'm going to talk about some technologies we can use in the present day to actually solve some issues around patient privacy. So next slide, please. So yeah, so briefly, what is machine learning? So with machine learning models, what we're trying to do is we're trying to model the relationship between data and the labels for that data. And the idea is that when we take data about real world use cases, like maybe in medicine, running through that data set, like Marble is the relationship between those input data points and these labels. So on the top left there, I've got a very, very simplistic data set, and it has a series of values for A, B, and the logical operation A and B. And whenever A and B are true, then the condition A and B is also true. So although I'd imagine not many of us have worked with logic before, I chose this condition because we all intuitively understand what this logical relationship is. We use it in language all the time. So the idea is our internal parameters of our model has this amazing sense of elasticity. So it's able to adjust and shift itself to accommodate the logical relationship between this data and the labels. Kind of like if you go to the dentist and you get a mold of your teeth done and you bite down on that putty, then that putty sort of sinks around the contours of your teeth. Similarly, models sort of sink around the contours of logical functions. So next slide, please. So this is as technical as it's going to get in this session, but this is one step deeper. So imagine we have our data, we have our labels out on the ends here, but we also have our predictions. So the idea is we can pass some data through our model parameters and we receive a prediction. But that prediction, if our model is untrained, might be completely wrong. So we want to figure out a way to find out how much we missed our labels with our prediction. And to do that, we use a thing called an objective function. And this is just like an accuracy measure of how our predictions compare to our label. And if we get a result from an objective function, then we can put this into an optimization algorithm. And this helps us to figure out which way we need to change our model parameters to make it give a better prediction. And let's say we had a very, very simple model with two parameters, and we plotted that on the Z and the X axis of a graph. And then we took the output of our objective function, so the criteria which we use to score our model, and we placed that on the Z axis as it corresponds to these model parameters. We'd have a graph which looked very similar to the one on the left here. And when we train our model, what we're actually doing is we're traversing that landscape in order to find the lowest possible point. And that's where the cost function is the lowest. So we've missed our prediction, or we've missed our labels with our prediction by the lowest possible amount. And this is called the global minimum. So that's the hardest slide here. So we can sort of move on to the next one, which is just a brief history of the data industry. And for the data industry to exist, for it to be in boom as it is now, there are three essential components, which are algorithms, computing power, and data. And we've had algorithms for the longest time. Neural networks, which are perceptrons, which are used in multi-layer neural networks, which are the quite complex models that we use today, have existed for over 50 years and date back to sort of Alan Turing times in sort of like the evolution of computing. So they've existed and we've had these in our possession for a long time. And then we move on to computing power, which is what's been the major blocker for actually using these algorithms on data because they're very computationally expensive to compute. But over the past 50 years, the number of transistors that we can fit on microchips has doubled every 2 years, meaning that we've now over the past 10 years, we've been in a place where we can actually perform data science using these models quite effectively and conveniently. And this is kind of marked by the introduction of these big cloud giants like Azure, Amazon Web Service, and Google Cloud, who kind of facilitate the availability of this core element, which is computing power. And finally, we need data in order to have an effective data industry. And the beginning of sort of this as of data as being very, very available has sort of happened over the last 20 years with the introduction of the second generation of the internet. So in Web 1.0, we had just very, very simple static web pages. And then this graduated to sort of social media and like the online shopping, which we know today, where we can go onto a website, we create an account, and we begin to create a digital footprint, which describes our online presence. And at this point, there are about 4 private entities tracking our whereabouts and our decision-making at any one time. And this is just to generate data during this social web 20 years. So the third phase of the internet is going to be the web of data, where the main use for the internet will be, instead of browsing web pages, it will be for sharing and communicating information or data. So over the past 10 years, we've had from 2 zettabytes of data we went from 2 zettabytes of data in global availability to about 64.2, which is outpacing Moore's law. But we still have this frontier of the healthcare sector and other sectors where the data that we have is extremely private, and so we can't get access. So we're missing that core component, which is that data. So next slide, please. So that's not to say that there aren't huge opportunities for us in healthcare. So these can be sort of summed up into these broad categories of supporting service delivery, supporting patients, and supporting research. So with service delivery, maybe it's deciding which is the most efficient hospital to place the MRI, or how can we allow patients to diagnose or find their own risk categories for given diseases. Or maybe it's about tracking the spread of certain diseases through epidemiology. Next slide. Having said this, there are huge impediments to these opportunities. For example, data sharing isn't possible due to regulation. And because nobody's sharing data, that means every individual institution has its own siloed data. And that data is biased to the demographics of their geography. And because this data has been siloed, there's no real incentive for there to be homogeneity in data formats. Meaning there are so many different formats people are storing their data that actually combining them at this stage is a real challenge in itself. In new governance, we have this notion of consent being harder to manage, where if I collect some data about some patients, and then I want to perform some new research task on that data, I need to go back and ensure that I have the consent of those patients for this new research purpose. And maintaining that governance is challenging and expensive. And then finally, up until now in the data industry, the general practice has been to just buy and sell data with no real concern for data subjects. And so data subjects are fairly reluctant to share their information at this stage without any guarantees as to their privacy. So then that brings us to the biggest issue with AI in healthcare. Next slide, please. Is that the data about the most important questions is the hardest data to access. So on the left here, I have a handwritten character which belongs to the MNIST dataset, which data scientists will train and benchmark their new approaches on, or maybe they'll learn data science with. And as a result, we can predict or we can classify these digits of handwritten characters with superhuman accuracy, if there is such a thing. At the same time, there are these very similar images around lung cancer scans, which technologically speaking, there's not anything more difficult about classifying a lung cancer scan than a handwritten character. But we can't do this problem very well because we don't have the availability. So if we can provide that availability, then we could solve medical style questions with the same level of accuracy as these MNIST models. Next slide, please. So what if we remove all the personal identifiable information? So this is the general requirement in HIPAA currently, but HIPAA was last revised 10 years ago. So this doesn't actually protect against the kinds of attacks on data that we have from this decade. So next slide, please. Once we have de-identified a data set, it's not too difficult to re-identify a data set. So the intuition here is that if I have a list of pieces of information about an individual, eventually that list is going to become long enough that it's unique. So, and then if I have some external data about this individual, then I can link that to the anonymized data and then re-anonymize or re-identify them. So in this case, we could infer that Jane Smith is married because we found the link up on that data there. So what if we can answer questions using data that we can't see? Next slide, please. So this is a slightly bigger question, because if we can answer questions using data we can't see, then we can solve this problem of availability for these X-ray scans. And the resounding answer to this is yes, we can see, we can solve questions using data we can't see. Next slide, please. And one of these techniques that we can use to do this is called federated analytics. It's kind of a fancy way of saying remote execution. So instead of having this, this data science setup where Joe, Jane, and Jack all have some data which I want to learn from, and I pull their data towards me, instead I can leave their data where it is. I can take my model, I can make 3 copies of it and send it out to where Joe, Jane, and Jack all are. They can all train their respective models on their respective data and send me back these updated models that I can then aggregate and turn into one central classifier, which has been trained on everybody's data. Similarly, I can use a thing called encrypted computation. Next slide, please. I don't know if there's any cryptographers in the audience, but I'll explain it from the start as well. So when I want to encrypt something, what I do is I take some plain to see information called plain text. I combine that with an encryption key and create a thing called a ciphertext. I can then send that to somebody and be ensured that the confidentiality of the original plain text is preserved because only they would have the key to unlock it. So with encrypted computation, we bump this up a level of usefulness because not only can we garble the information so nobody can read it, but whilst that information is garbled, we can still perform mathematical operations on that data or that ciphertext. So that means if I have a number 1, I encrypt it, I have another number 1, I encrypt it, I add those ciphertexts together, decrypt that ciphertext, I would get 2. So this lets us actually take encrypted data, send it off, make a prediction with that encrypted data, and that prediction result would remain encrypted. And we can send that back to the client or the patient, and they can see whether they, let's say, are in a high-risk category for non-alcoholic fatty liver disease or not, and receive this service without ever exposing any of their data in the first place. So if we can't see the data when we perform operations, is it safe? Next slide, please. Maybe just skip this one as well. Okay, perfect. And the answer is no, not quite. So there is this notion of reconstruction when it comes to a piece of private information, which we can query certain attributes about, but not the information itself. So this is essentially the problem that we have when we compute analytics on some private data, is that the computed result might release some information about the underlying data. And this is quite abstract, but I'm sure everybody's aware of the game Wordle. It sort of took the world by storm a couple of years ago. What we can do is we have this unknown 5-letter word, and we can guess 5-letter words, and it'll let us know which characters are in common with the one that we're trying to guess. And eventually, once we've guessed enough letters, we can begin to build up enough constraints that we can find a unique solution for that word. And this is exactly what we're doing with reconstruction. And it turns out computer algorithms can do this really, really well. So this slide here is amalgamation. Next slide, please. This slide here is an amalgamation of 2 different research papers. So the first one is where this table on the left belongs to. And this is a bunch of privacy researchers had generated a fake block on the US Census so they could try and do a reconstruction attack on it. And they had computed a series of different metrics, which were count, median, and mean. And they did this on a bunch of different cohorts. And if any cohort didn't have enough people in it, then they would redact it. So with just the information which is held on that table to your left, they were able to build 164 equations which represented satisfiability constraints and they were able to solve these equations to make a unique inference on what the values were for every individual from the block within 0.2 seconds. So the second paper I'm going to talk about in this slide is when the US Census Bureau took a look at this original paper and they applied it to their 2010 release statistics. What they found was they were able to recreate around 70% of the US population on where their block was, what race they were, what age they were, what sex they were, and what their ethnicity was. So this is a serious problem. And this is the final technology which I'll be speaking to you about today. Next slide, please. Which is differential privacy. And the goal of differential privacy is to protect against this, this reconstruction style attack, where there's information that gets released within a query. And the idea is we apply some degree of plausible deniability for the individual which went into that, that function. We sort of measure privacy with this notion of this thing called sensitivity. So we measure sensitivity of a function with, let's say we take two data sets, a data set and data set prime. The difference between data set and data set prime is that data set prime has had one row removed, as you can see on the right there. And a perfectly private function would give the same result regardless whether it was computing D or D prime. And usually what happens is there is a slight difference in sensitivity, and we scale a degree of noise to that difference in sensitivity. So to give a very intuitive example of how this works, let's say we're epidemiologists and we're taking a survey from a population, which is just yes or no answer. Do you have, let's say, some shameful disease? And the next slide, please. And let's say that a large number of the cohort aren't going to answer truthfully because they don't want to have their answer correlated to them. So I can say, well, pick your answer in your head of your truthful answer and flip a coin twice. If on the first flip, the coin is heads, then give me the truthful answer. And if on the second flip, it's heads, then give me the truthful answer. But if it's tails on both flips, then you can flip your answer and lie to me. So 75% of the statistics will be correct answer, but 25 of these statistics will be a lie, which gives every individual in the cohort some plausible deniability. So I can't ever link it with their answer back to them. At the same time, as the set in the survey grows, the distribution of that 25% who lied will more and more closely match the distribution of truthful answers. So I can get pretty good statistics as an epidemiologist, but I don't actually have to sacrifice the privacy of the individuals. I can guarantee a better turnout. So just briefly to recap, we have a data industry which is in boom. There are lots of opportunities and challenges in the health industry for this. And over the past 4 years or so, we have been able to, or a bunch of techniques have been popularized, which allow us to sort of put an end to this trade-off between the availability of data and the potential privacy or usefulness of it, which has led to the data industry not quite getting into the healthcare industry just yet. So thanks. And with that, I will hand back over to Dr. Mystery. And yeah.
Thank you, Adam. And I got to say, you did a great job in explaining really technical information to people like myself who are the lay public when it actually comes to this level of technology. And I think I found this good slide just to recap, where we take all these factors on the left-hand side, really, really complex network of factors from genetic and environmental and the microbiome and lifestyle, etc. And we put it into this machine with all these algorithms and machine learning, etc. And the output that we're really excited about, Unlikely Bedfellows, a tech company and a patient advocacy organization in liver health, we come up with these models of personalizing options for patients, risk stratification, environmental control measures, and ultimately, how can we influence policy from all of this? So with that, we're going to go into the discussion, but I'm going to turn to Adam and Anne for the first question that I want to put out there. You know, and this happens often to me as a doctor, where I present all the data to a patient, and then the patient looks at me and says, "So, doc, what do you really think I should do?" Right? And so we've gone through re-identification and reconstruction, the federated analytics, encrypted computation, etc. But there's always this lingering fear of the ghost in the machine that's going to take over, or what Big Brother is going to do with data. So I'm asking you, our tech doctors, where are we standing on this when it comes to privacy? How are you feeling about it?
Go ahead, Anne.
I guess I can give some context on what I'm seeing regulatorily and generally in governance, and then Adam, maybe you can answer like kind of the different techniques that we see developing in the space of privacy preserving machine learning, because it's moving really quickly, I think, outpacing really what governance and regulation has. So I think this was mentioned a couple of times that like HIPAA is not super comprehensive in being able to protect patient privacy. It's about patient portability is kind of the spirit of HIPAA, but people always reference it as something that protects patient privacy. And so I think the regulation is a little behind, but trying to get ahead now with more detailed regulation like GDPR and CCPA that we see. And this has been true for the past, I would say, like 8 years, that the application of GDPR and CCPA has been trying to be applied, but we still see a little bit of a lag, which is why I think it's very important for technologists and also physicians to come together and have some consensus about what are the trade-offs between utility of patient data and also being able to protect patient privacy and trust. And so that's why, you know, Array Insights, our company, is working with the Fatty Liver Foundation and many other patient advocacy groups like them, because it's going to be very unique for every disease. And the Fatty Liver Foundation is experts in the idiosyncrasies of what is really important from a research objective for patients and their care, and how we can help. Adam?
Yeah. So I suppose to respond on the point of how do we know that Big Brother isn't watching when we submit our data currently? And I would say that at the moment, with the exception of GDPR, and I'll maybe come back to GDPR in a second. At the moment, it's a Wild West. There's all the regulation that we have at the moment is not fit for the kind of attacks that I was describing there, and a plethora of other attacks like similar to that. So yeah, at the moment, unless we have conscientious companies who try and fill that gap of privacy, which isn't being filled at the moment, yeah, we probably shouldn't submit our data at the moment because we will become the product. Until legislation and governance catches up and makes their significant business disadvantages to not respecting patient consent and privacy, then we're going to continue to see this. And I'll get back now to GDPR. So GDPR has attempted this, but it has done it with all the force of a wet flannel. It's I don't think any large tech giants have been taken into account in recent history or ever, despite Mozilla actually lobbying GDPR over the use of data by Chrome. And including this, I think the biggest department for enforcing GDPR is in the UK, and I think they employ 10 technologists. So we have this massive set of technological capabilities of how we can subvert people's attempts to de-anonymize data and so on. And we have this lagging governance, which is stopping people from, not stopping, but isn't incentivizing people to protect against these vulnerabilities. So right now, Big Brother is watching us, but hopefully within the next few years, we will be able to create some systems which will make that impossible, or at least enshrine the patient's right to privacy.
So I'm feeling somewhat comfortable from my tech doctor's advice, and you know, I think it's a work in progress. From what I understand, we're moving together the technology forward together with the policy, as well as the engagement with data, right from the patient perspective to health systems, etc. And it's all happening at the same time, at different rates. But I'm feeling comfortable that Big Brother is also looking out for us rather than to take advantage of us. So that's a good thing in the policy landscape. And I am thankful for people like you who are working to ensure that there are ways of protecting patient confidentiality, if not only from the policy angle, but in the encryption and the technology side, in order for that to happen. And so I want to, for all our attendees on the call, you know, we throwing out around some discussion questions, but feel free to put your questions in the question and answer box as well, and we can get to them as they relate to the work that we're doing. So something that Adam, you talked about is models aren't set in stone. There's a malleability about it. There's a dynamic feedback loop in it. As and when it grows and learns more, the model changes and tweaks. So can you tell us how over time that would actually engage with our patient population that is changing? You know, we're excited for the fact that we may have a new drug soon for NASH or NAFLD. How does that actually factor into the change in the model? Or there may be a ban on certain type of foods that impact patients' health, etc. So I want it from that point of view, and then I want also Wayne to chime in on how we continue that patient engagement as things change in the environment and the landscape and policy.
Yeah, sure. Yes, models are extremely elastic and have the ability to train and be retrained over time. So in terms of how this relates to the patient cohort, as the patient cohort grows, then the model we built to answer a very particular problem will, in theory, get better, at least get better fitted to the larger population. The quality of the model will get better. However, if we begin to change the underlying sort of, I suppose, logic of the data that we've gathered, whether if there are certain foods which get banned, and this creates a noticeable result in how the disease is expressed, then we can't then adapt a previous model to then be better at predicting this new case. There is this notion of transfer learning, but it's a slightly different kettle of fish. So usually when we have a new set of data or a new set of features, we train in a completely new model on that new feature set, just to make sure that what holds for the first instance of that data also holds for the last instance of that data.
Well,
I think
following on to these experts is always interesting. You know, one of the biggest problems we have is trying to educate our population, and you know, that's a challenge, both from the issues of the disease, but one of the things that engages the patient community so much is, you know, treatments and and things that they can do, and how to understand how it all fits together. But one of the things that that really interests me, and I wonder, Anne, if you might be able to shed some light on it, is that we're being blasted every day with news about AI, and they talk about machine learning. Now we're, I think, talking about machine learning here, but I wonder if you could give us a sense of what AI really means, what machine learning really means, how they overlap, and how they might apply to our community as these things develop.
Yeah, so I think like with any technology, we should see them as tools, as opposed to the other way around, right? That the idea that AI would replace a doctor's advice, I think we're still kind of far from that. not necessarily from a technological standpoint, but from like an emotional standpoint. I think the trust between a physician and a patient is extremely important and should not be underestimated. And so I would say that for technologists like us, it's really important, again, to just repeat what I mentioned before, to partner with physicians to create tools that use AI that can be, at the end of the day, determined by a doctor of like what makes sense and what doesn't make sense. Because I think there's always going to be limitations of data and idiosyncrasies of a particular patient's not only interest in outcome, but also preference for treatment is very subtle and oftentimes like not really found in these models. I think a really easy example to point to is like hospice care. I have no idea how that could possibly be triaged to a machine learning model exclusively, when I think there's a lot to be said about, you know, just sentiment analysis when you're interacting with a patient between, you know, doctor and patient and trying to figure out what the best course of action is. And so to answer your question, like, yeah, I think we're still pretty far, and machine learning might technically supersede and have like superhuman abilities to do simple tasks, but I think we should always see it as more of a tool. And I'd be kind of curious to hear Dr. Mistry's perspective on this as well. I'm sure that there are new introductions into clinic all the time of different technologies, and what he's seen like sort of succeed and fail. I have some references that I have for like ICU management, and again, it just points to this empirical kind of pattern where we see that tools that are too AI driven are never used and like have poor interfacing. And then if you have just the right amount of AI with humans in the loop, then you have this like perfect concert of what can be coordinated in order to improve patient care. But Dr. Mistry, please.
And that's a really important question. And you know, it's interesting because in an academic environment now, there's a lot of emphasis on transdisciplinary research or transformative research. And that's not looking at a solution or an approach from a particular disciplinary lens. So it's not just medical, it's not just social, it's not just anthropological or technological, but how do we actually find the sweet spot where all of those intersect? And it varies by case, you know, I mean, and it varies by individual as well. And so I think what's important from a practitioner point of view, a physician point of view, is that we need a toolbox with a whole lot of different tools. And it's almost the art of the physician where we can read our patients and then choose the right tool for them. And I know some patients of mine, they just want an app that's going to tell them and ping them every hour on what they need to do for their diet and their lifestyle. And there's some patients that just need a really nice sympathetic ear from their care provider. And some patients just need sort of coaching type of thing. So I think it's important for us to have that tool. But where I think AI and machine learning is absolutely critical is when we think more systemically, like hospital management and looking at resource allocation and that type of thing, where we need that data to optimize systems the way they function. And so from that point of view, I think it's really important. And so I think fit for purpose is the motto I would go with when we think about adoption of technology in a clinical context, in a health management context, and ultimately in a health policy context. Does that make sense? Yeah. Okay. So let's, I think that's a good segue into us going into a more clinical realm. And I think as patient advocates, we're not just dealing at a clinical level, but we're dealing at a preclinical level, which is the societal level. And so if we had to put our heads together on, wow, we're starting to deal with many patient data sets. And at the Fatty Liver Foundation, we did patient screening where we looked at staging of liver disease, fatty liver disease. And we did sort of a very high level back of the envelope, collecting data on age, ethnicity, the type of lifestyle, the weight, waist circumference, etc. And we started sort of seeing patterns emerge from that. But when we start going even deeper into it with bigger data sets, what might the future look like in patient care at the preclinical level as well as the clinical level? And let me turn that to both our technology people as well as our patient advocates. And Henry, feel free to chime in as well. Wayne, do you want to kick that off? And then I can turn to Adam as well.
Yeah, well, that's a really multi-headed question, because there are forces from all directions that we have to cope with as we think about how we engage patients, how we treat patients as they enter medicine, how the medicine respond, how medical systems respond to them. What does the patient take away from the interaction with physicians, and can they apply it? And we have every conceivable case or route of circumstances that people can find themselves in. And one of the greatest challenges that we have, I think, is to be sympathetic to all of the personal realities of the lives people live, because these diseases affect people in a lot of different ways, and they struggle with a lot of different kinds of problems. And we can't invent a shoebox that we put everybody into the same category. And I think one of the great promises of this kind of tooling is that it can become individualized. It has the potential to become a really personal servant, if you will, of the patient. And I view it from a patient perspective, not a physician. You know, I hope that the doctor uses tools in a good way for me, but the thing that I want is support for the things that are important to me and how I live my life day to day.
Adam, over to you.
Yeah, sure. So how I think this is going to look from a clinical level and a preclinical level is I think there's going to be one innovation which is going to really shake things up and disrupt how data is managed currently. And the innovation already exists, and it's the ability for patients to hold all of their medical history in their own possession, which means, and the technology which could manage this is this new form of like, I'm sure we all know HTTP. I'm trying not to get too technical in this description, but it's a new way of managing trust online called decentralized identity. And specifically the technology that I'm talking about just now is trust over IP. So I could, in theory, have all of my data held in a thing called an agent, which manages all my verifiable credentials. And then I could then go into my doctor's office. I could have an app on my phone which talks to this agent, and it would say, I want to give access to the doctor these set of features about me, so they can put it into their tool to make a prediction about my outcome for something. And it could be that there is a library of these tools which can take in data and make a prediction. So then I can show the QR code that's presented on my phone. I can then give that to the doctor, who will then take that QR code, which gives their agent a URL to my agent. I can then present a bunch of proofs around the veracity of my medical information to that doctor. That doctor can then send the model to my agent, and they can make a prediction, and I get the result back to me. So to try and, I went a little bit technical there, but to sort of step it back a little bit, we could have our own personal data stores, which could be queried by anyone given our permission. and we can prove any element of information about these credentials or this data store that we've been given. So yeah, I think that all the data about an individual at consultation time will be made available by the patient, and the doctor will be allowed to process it and look at it to give them fine-tuned results. And similarly, when the doctor takes blood or does tests on a patient, instead of giving them a piece of paper in a little booklet which has their test results, they can pass that to the patient as a credential that goes into their personal data wallet. So that's the way that I see this going in about 10 years. And I think we're in that transitory phase just now where people are beginning to adopt this new technology, trust over IP, which facilitates that. That's not to say people haven't already begun using it. There's a company called MedCreds, which currently manages credentials for doctors using this approach. So yeah, this transformation has begun. And a series of my earlier publications have been about catalyzing that process.
Yeah, and I'll just add really quickly, I totally agree with Adam's vision for the future of data sharing and like patient data privacy. In my own sort of like personal work, I'm doing zero knowledge proofs on DNA for this like security conference this summer. And so I feel like the technology exists and people are definitely pushing the limits of that. I think it's just a matter of regulation catching up to it and communicating with people on webinars like this on what is possible in order so that they can put in place systems, whether it's like driven by government or patient advocacy or other types of governance in order to phase out what the rollout of patient data privacy looks like, whether you are creating in some ways a data cooperative or a data union across patients or a federation, and then having patients individually manage that and then manage that not only in their membership in a patient group or as an individual. I think it just has layers of complexity that I'm really excited to see the adoption of over the next like 10 years.
That's very exciting, and I have goosebumps from the excitement and also my cautions as a physician. There is something about similar to blockchain on how data is stored in different places. But I think one of the things that you said was very exciting for me is the empowerment that a patient goes through when they have access to their knowledge, their medical history, etc., is phenomenal. And we've seen this from very rural, remote areas across Africa where patients have a card of their immunization and their weight growth charts to complex electronic medical records. When patients have access to that, it is very empowering. I want to ask just for 5 minutes from our attendees. We are wrapping up now, but I want to come back to the question of this webinar. Is it helpful or is it hurtful? Your final comment on that, and then you get to make one wish for the future of this sort of technology and health collaboration to put out there. And let me start with Adam, and then Anne, and then Wayne, you can close off.
Yeah, okay. So yeah, I think it has the massive potential to be extremely helpful. I think it could potentially be as effective as like the printing press was to the spread of education. At the moment, I think the biggest issue is a lack of governance, which keeps people from using data responsibly. And if I were to make a wish, it would be that the world catches up, or we can keep pace with the state of electronic advancements, so that we don't end up in the situation that we're in currently with data and how it's governed.
I have the same exact response and wish.
Oh my. I think that it's important that patients begin to understand some more about this, because we're pummeled by the news, and we're concerned by the things that we see in the news, and I think that that's very off-putting for the patient community, because we already have a fear of privacy violations, being taken advantage of and being given bad advice and bad medicines and all of the things that we worry about. So I wish that in all of the development of these tools, that the patient centric view of them stays constant, that they really focus on patient needs and bring the medical establishment, the regulatory folks to us, rather than just using us as the cannon fodder to see what works.
Thank you, Wayne, and thank you, our panelists, for sort of making this knowledge and information so accessible to us, and sort of starting to paint that picture on what the future might look like with this collaboration. And I think just finally, from my point of view, communication. And as long as we keep talking, we can sort of allay fears and concerns and also take advantage of opportunities on webinars like this. So just to recap, there will be a recording of this that we'll distribute, and look forward to continuing the conversation. So thank you so much.
Thank you.
Thank you.